Okay, so welcome to our lecture number 7 in this course in Algebraic Topology. I'm Norman Wildberger at the University of New South Wales. So last time we talked about the Mobius band in the context of a non-orientable surface. Today what we're going to do is we're going to talk mostly about two important non-orientable surfaces which don't have boundary, the Klein bottle and the projective plane. The Klein bottle is a bit of a curiosity. The projective plane is a really fundamental object in mathematics. Before I do that, I want to give you an example of the Mobius band as a moduli space. That's roughly meaning a space of possibilities. So what I want to consider is, let's let M be the space of all lines in the plane. So we take our usual plane, A2, and we're considering all the lines in the plane. And what we'd like to do is we'd like to understand that as a space of all lines. Okay, so I'm just going to give you the idea and you can sort of think about it. So I claim that this space of all lines is really like a Mobius band. It's kind of like an open Mobius band. Why is that? Well, it's because if you have any line in space and we want to classify them, one natural way to do that is to group them together in terms of their directions. Okay? So if we choose this particular direction, say that one there, then there's going to be a family of parallel lines in the same direction, and the numbers of lines or the parameterization of all those parallel lines is just a line itself. So there is a line, say an A1, of lines parallel to any given line L. So if we started with that line L, then there's an A1 of lines parallel to L. Now how many directions are there for the line L? Well, there is an S1 of possible directions for L. Why is that? Well, I have to remind you that the space of all possible directions in the plane is what we called the projective line. All possible directions is represented by all possible one-dimensional subspaces, and that was what we called the projective line. And we saw that the projective line was topologically the same as a circle. One way of thinking about that is because it's represented by that displaced line plus an extra point at infinity corresponding to the horizontal line. So if we put these two facts together, it seems that the moduli space of all possible lines is like some kind of product between a circle and a line. For every point on a circle, we have a line of possibilities. But then we think, well, so for every circle of possible directions, there's going to be a line of possible lines parallel to that direction. That's like an open interval associated to a direction. So one possibility is that as we go around, we get a cylinder. That's not necessarily the answer, but that's at least a possible way of combining a circle of lines together to form an object. Or another way of doing it is to take our base circle and to have our interval go around, but with a twist. Okay, so maybe at the back here we'll this way. We'll twist as we go around. And that means that we're really talking about a Mobius band. So which of these two possibilities is it? So here's our Mobius band drawn a little bit nicer. We have to ask ourselves, is there a property that the Mobius band has that the cylinder doesn't have? Well, how can we tell these things apart topologically? And one nice way of telling the cylinder apart from the Mobius band is using the idea of genus. Remember, the way we distinguished between toruses is we drew a little loop and asked, can we separate the space with a loop? Now, any loop that we draw on the cylinder is going to separate it. You see that? Even if we draw it all the way around. Any loop is going to separate it. So the cylinder has genus 0. We can't draw any loops which keep it connected. Remember, the genus is the maximum number of loops that we can draw, which are non-intersecting and which don't separate the space. What about the Mobius band? Can we draw a loop that doesn't separate it? Well, I showed you how to do that. Just the center loop. If we just draw the center loop and we cut along that center loop, I already did it, we saw that we don't get a separated space. So this thing has genus equal to 1. So we could ask over here, in terms of the space of all lines, is this going to be of genus 0 or is it going to be of genus 1? Can we draw a loop of lines which doesn't separate the space?
If once you've done that one line through the center, and you've got a new Mobius band, you can do another line through it.
It's not actually a Mobius band. There's two twists. It's a little bit different. Okay, so here's a loop of lines. Okay, here's our A2. All right. So let's start with that line. And now I'm going to consider this whole family of lines. I'm just going to rotate that line around some fixed point. And I'm going to get eventually back to where I started. That's a loop of lines. That's a loop in the moduli space of lines. Okay. That's a loop of lines. Doesn't look like it, because each one of those lines is distinct from each other, right? They're all different, and they're varying continuously, and we're starting at the same place that we're ending up. So that's a loop. Okay. So now the question is, does that loop separate the space into two pieces? I claim that this loop does not separate. The space. We're calling it M. What does that mean? Well, it means that if we take any two points in our space which are distinct from the loop, that we can go from one point to the other in a continuous way, avoiding the loop. Okay, what does that mean in terms of this context? Well, it means that if you take any two lines, say M1 and M2, that we can go continuously from M1 to M2, avoiding all the points in our loop. Can you see how to do that? Well, let's suppose that M1 and M2 meet down here somewhere. A naive thing would be, okay, to go from M1 to M2, I'll just go like this. I'll just rotate around that intersection point. That's a continuous path from M1 to M2. Does it pass through the loop? Yes, it does, because in this particular case, well, that point there is in the way, and so I'm going to eventually cross that, and I'm going to be actually touching the loop, so that's not allowed. That's not a good way to go from M1 to M2. But there's another way to go from M1 to M2, which is to rotate in the other direction. We can rotate this way. So we can take the line and we can move it continuously like this. This rotation goes from M1 to M2. It's a continuous path of lines that connects arbitrary 2 points and avoids the loop. So it shows that what we get when we cut out this loop is still connected. This loop does not separate the space, so therefore the genus is, well, at least 1. So it can't be a cylinder, so M is, okay, a Mobius band. Rough argument. So an object that you've been looking at for years in linear algebra, just a set of all lines in the plane. Topologically, it's an open Mobius band. In particular, it's non-orientable. Okay, so now let's have a look at the Klein bottle. The Klein bottle is what we get if we take a square or a rectangle perhaps and glue those two sides together, just like what we're doing when we do a torus. And then we glue these two sides together, but we do so in the opposite way from what we do when we glue a torus together. The first identification results in a cylinder. That's dotted there. That's after we've glued, say, A with A. So there's A. And now this B and this B still have to be glued together. So what do they look like? Well, if that one's in that direction, then this one's going to be in this direction. Okay, last time what we did is we, with the torus, the orientations were different. We could just put these two together like this and they would match up. We're not allowed to do that in this case because then the orientations on these two boundary pieces are going to be opposite now. So what we have to do is we have to, well, what we can do is we can maybe enlarge that for a little bit and then take this part here and bring it through itself. You kind of just have to imagine this tube, we're making it longer, and then as we bring it through itself, then now this thing is like this. Can you see that? If I take that tube there and I bend it like this, it's going up around here like this. So when it's over like this, that's the side of it. It's going to be going down like that, right? So now all what I need to do is just glue this to that from the inside. Okay. So that's called a Klein bottle. And first introduced by Klein. In fact, Klein introduced it in a different way. Klein introduced it as two Mobius bands glued together. A Mobius band has a circular boundary. So if we take two Mobius bands, then we have two circular boundaries. And we can just label each one of them 0 to 1, and then we can glue according to those labels. At least abstractly we can do that. So I want to show you how we can see that, just without making complicated models, but just really working with this basic square or rectangle with sides identified.
And gluing the Mobius band to the chiral, the other top?
That's a good question. I guess one should say that homeomorphically they're the same. The chirality is a manifestation of their appearance in three-dimensional space. But as topological spaces, there's really only one Mobius band. You can still bijectively make the two different chiral Mobius bands connect with the bijection. All right, so here's how we let's dissect a Klein bottle, and we'll just draw this picture a little bit bigger. So there will still be our top and bottom. And now I'm going to divide this into three pieces. And let me call that X, Y, and Z. And then pieces over here will be X, Y, and Z. And let's call these three regions 1, 2, and 3. And maybe that's still A and that's still A. And that's still our Klein bottle. And now I'm going to remove this piece here. What is that? That piece number 2 has an identification there and there, but these edges are just free. So that's a Mobius band. Okay, what about 1 and 3? Well, we have to put 1 and 3 together. And how are we supposed to do that? Well, we're supposed to glue this lower edge here to this top edge here according to the edge identification A. So what we're going to do is we'll take our piece number 3 and put it on top of piece number 1 so that the edge A, the common edge A, that is being glued together. Okay, now what does the rest of it look like? So this is number 3, so there's an X over here and a Z over here. And piece number 1 had a Z over here and an X over here. Well, we've glued that internal edge A, it disappears. So what we end up with just is a rectangle with the top and bottom free. That's a boundary. And this edge right here, we can just replace it with, say, C. It's the edge starting with Z and then going X. And here we have Z and X going in this direction. So that's also C in the opposite direction. And that's also a Mobius band. So we've cut up our Klein bottle into 2 Mobius bands. Okay, and our second, that's actually a closed surface, the Klein bottle, right? It has no boundary, because we've glued all the boundaries together. The other important one is the projective plane. And this is just a direct two-dimensional analog of the projective line. So topologically, it just amounts to, we're looking at the space of one-dimensional subspaces of a three-dimensional space. And we should give it a name, P2. One-dimensional subspaces of three-dimensional space. So I have to just remind you that P1 was one-dimensional subspaces of A2, of two-dimensional space. We had a picture of that in the previous lecture. And that was the same as a circle. So now we have to think about three-dimensional space and lines through the origin for that. Now this is very important, a mathematical object, because it really explains the basis for projective geometry. This is the fundamental building block of projective planar geometry. And we talked a little bit about projective geometry, but the historical version of that was that the projective plane, P2, was really the ordinary plane, A2, together with a line at infinity. Together with, union say, P1, a line at infinity. And 17th century geometers thought of the standard Euclidean plane together with a rather mysterious line at infinity. It was a little bit hard to understand. What they thought of is if you have any two parallel lines, then those two parallel lines will meet at exactly one point at this line at infinity. That's the projective plane, the way that it was historically thought about. And then in the 19th century, there was a dramatic revolution about the thinking, and it was realized that there was an alternate description of this projective plane purely in terms of one-dimensional subspaces of three-dimensional space. A very important, profound realization. That the same object is occurring when we look at all lines through the origin in three-dimensional space. And why is it the same? It's not hard to see it's the same. The clue is to look at an auxiliary plane. The plane when, say, z equals 1. Every line through the origin will meet that plane z equals 1 at a distinguished point, except for the horizontal lines. The lines which lie in the xy plane themselves. So in this picture there are two types of one-dimensional subspaces or lines through the origin. The ones which are horizontal, which are themselves just a P1, same picture of the projective line. And all the ones which are not horizontal, well, if it's not horizontal, it means that it will eventually meet this plane in exactly one point. And points in this plane, this reference plane or auxiliary plane, exactly label the non-horizontal lines. So in here, we are seeing the non-horizontal lines or one-dimensional subspaces. And here we're seeing the horizontal ones. And here that's an A2 of possibilities because that's a plane. And that there is, well, that's a projective line. That's a P1. So these two, this is really a better explanation of what the classical projective geometers had been studying for centuries without really knowing it. All right, this is described in more detail in my series in the Wildberger series. I have about 10 videos on projective geometry where this and other things are explained in greater depth. But we're just going to be interested in this P2 as a topological space. So how does that look? We still don't really know what it looks like. So the key to understanding it in terms of a topological space is to introduce a sphere. So to visualize P2, we introduce unit sphere, S2. So let's do that over here. So there's X, Y, and Z. There's our unit sphere. There's the equator, which is horizontal. This gives us another way of thinking about lines through the origin, because every line through the origin will meet this sphere in 2 points. In fact, 2 antipodal points. It means opposite points. So this is a line L, and it meets the sphere in 2 antipodal or opposite points. So another way of thinking about what the projective plane is that it's what you get when you take the sphere and you identify opposite points. So you're taking the 2 sphere and you're identifying 2 points that are related by the negation map, just multiplying by -1 in the space. So which we can write as, okay, it's a little group with 2 elements, plus and minus 1. It sends a vector v to minus v. We're identifying those. Now, if we're identifying those, then it's a little bit simpler. We could say, well, why don't we just restrict ourselves to the northern hemisphere, to the top of the sphere. Okay. So if we just restrict ourselves to the top of the sphere, then we can say that this is the same as the top hemisphere. Let's draw that again. So there it is there. Here's the top hemisphere with the equator down at the bottom. What do we have to do to make this into the projective plane? We still have to identify opposite points. Now we've taken care of all the points which are strictly above, but we haven't taken care of the opposite points on the equator itself. We still have to identify this point with its negative, which is also horizontal, going through the origin, which is down here in the center of the sphere. Right? So that's a vector v. Then minus v itself has to, these points have to be identified because they represent the same line through the origin. So we must, it's the top hemisphere with boundary points. Maybe I should say with antipodal boundary points. Antipodal boundary points identified. Okay, so how does that identification work? Well, let's just take that top hemisphere, which is like a cap, okay, and we'll just flatten it out. Now it's a disk. And what do we have to do? We have to identify this point with this point. There's V, there's minus V. We have to identify this point with this point, and so on. So it means what we really need to do is we need to glue the two sides of the disk together in a rather unorthodox way. Now it's a completely planar situation. We've gone from the three-dimensional space of lines. Now we just have a single disk. It's just a disk in the plane. And if we introduce a north and a south like that, then we can describe this gluing by saying, well, we need to glue that side to that side in that order, so that this point is glued to that one, and as we go down here we glue. So there's really only, it's a kind of a simple thing. There's really only two sides, A and A. Now you could get yourself a little disc made out of cloth, and you could get a needle and thread, and you could start sewing. Okay? How would we sew this? We would take this point and we'd sew it together. So we take these 2 points and we'd sew it together. But we kind of have to twist things because this point here has got to be sewn to that one there. So we have to sort of twist this over. And you can start sewing, and you get about halfway when you start to realize that this is kind of getting knotted. You're not going to be able to finish. It's an excellent exercise to try this actually with just a hat or something, a cloth hat, and just see how much of it you can identify. You're just getting a hat, and you just fold that over there, and then you fold that over there. You have to see how much of it you can do. You can't do all of it because this is not a surface that's visible in three-dimensional space as a proper surface. This formulation in terms of a disk, there's a variant which perhaps makes it a little bit more like the other ones that we've been looking at. So here's a variant. We can make a square. You use a square instead of a circle. So if we're going to use a square instead of a circle, then there's got to be, we'll think of this as being one side and this as being the other side. Okay? So instead of having A and A, we'll now have A and B. And on the other side, also A and B. Okay? I'm just doing this instead of having a single A. That was really going all the way. That's one edge, has to be glued to that edge. Okay, so I propose to play the same trick that we did for the Klein bottle on this thing and decompose it. So what we're going to do is we're going to cut out a Mobius band. So let's cut out a Mobius band. So we'll take that square and make two cuts like this. There's still B here and B in the opposite direction here. And now instead of having a single A, I'll have maybe X, Y, and Z. And over here we'll have X, Y, and Z. So X, Y, and Z replaces what was A before. And I have three regions, so I'll call them 1, 2, and 3. And the first thing we'll do is we'll take out the middle region. Because we're just cutting it. So So when we take that thing out and look at it, there's a y there and a y there. That's number 2 that we've taken out. That's a Mobius band. Which, by the way, immediately tells us that the projective plane is not orientable, because it's got a Mobius band sitting inside it. So even if you just restrict yourself into this Mobius band, the non-orientability is already there. So this whole surface is non-orientable. Okay, what about the rest? You have this Mobius band, and then we still have 3 and 1. And we'll play the same thing that we did with the Klein bottle. We'll put one on top of the other. So we'll get 3 there and 1 there, glued along the common surface B. But I'm going to have to do something a little bit here to this to make them match up, because this B cut goes this way, and this B cut goes this way. So I'm going to glue them along the common boundary B like this. So I'm going to take piece number 1, and I'm just going to translate it exactly. There's still Z, and there's still X. But what have I done to number 3? I've had to flip it over to get it in the right position so I can do the gluing. And that means that the X piece now, okay, I've taken it and I've flipped it over like that. The X piece is now over here. And the Z piece is over here. What is that? It's a kind of a curious thing. We have Z here and Z coming in like that. What does that do for us? Remember, we have to glue those two things together. So I'm going to take this and I'm just going to modify it a little bit. Make it look like this. So there's Z, and there's Z, and there's X. Oh, sorry, the other way. X and X. These gluing instructions telling us that we have to glue this to this, this to this. We have to glue these two things together. So we just have a little seam, and we're gluing it together like fixing a rip in your shirt. And same thing here, we just glue these two together, one by one. And when we do that, what we get is that top piece and that bottom piece. And now there are no more edges that are free, that need to be glued. It's fixed, it's finished. And what is this thing? It's just a disk. It's just a disk. And so that's telling us, therefore, that the projective plane is topologically a Mobius band with a disk glued on its boundary. Union disk. So it's what you would get if you take the Mobius band and you took a disk and you just glued the disk to the Mobius band along the circle all the way around. When you've finished, that's it. That's the projective plane. All right, so these are some of the basic ingredients for our assault on the classification of surfaces. There's going to be a few more things that happen. But we're going to take a detour next time. We'll go back to the ancient Greeks and talk about Platonic solids, Archimedean solids, polyhedra. We want to connect the continuous with the discrete. We're going to do counting. All right. So back to the ancient Greeks next time. See you then.